Hi, this is a short video to help you out with lab number 2 for those of you who haven't finished it. About the decoder and implementing a function with the decoder. It's quite simple once you realize that a decoder, so here I'm going to draw a 2 to 4 decoder. There's two inputs, say A1, A0, and it has 4 outputs. That's typical, doesn't have to be that way, and this one doesn't have an enable. So what you must remember is that the decoder generates all the minterms of a function. And the minterm is just a function that is 1 for one particular combination of inputs. So if I have A1, A0 can be in all these 4 combinations. Then the output Y0, which is minterm 0, is going to be 1 in this case and 0 everywhere else. And minterm 1 is going to be 1 in this case and 0 everywhere else. Minterm 2 and minterm 3. So that's what the minterm is, and it just happens to be Y0, Y1, Y2, Y3. So you see the decoding part in the sense that 0, 1 and 1, 0 in binary is 2, and it's Y2 that is being active. Okay, so if you have a function f and it's expressed, say, let's assume that its minterm canonical form is 1, 3, and you want to implement it, well, that's M1 or M3, and you have these available right here, so you can just take M1, M3, or them together, and that's it. You have F. All right, so let's assume that instead of that, I have a decoder that has enable active low outputs. So I'm going to put little circles here. Okay, and we're going to say that this is Y0 bar, Y1 bar. That's a convention. We're going to put bars over the outputs to indicate that they are active low, even though the circle already indicates that. And I have minterm 0 bar, minterm 1, minterm 2, minterm 3. I should erase this because this doesn't work anymore. All right. What we saw in class is that the minterm canonical form is one way to express a function, but we could also express it as a max term canonical form. And all the max terms that we're going to find in that expression are the indexes that do not appear in the minterm form. So 0, 2. And so I'm going to erase this, erase this, erase this, erase this. The other thing we know is that max term I is minterm I bar. It's the opposite. So what we have here is we have max term 0, max term 1, max term 2, max term 3, and these are the opposites of minterm 0, 1, 2, 3, and you see because we've inverted the output. So if I want to express my function now, it should be the product of max term 0 and 2. So I can take, max term 2, max term 0, put them in an and then I have F, which is max term 0 and max term 2. All right, so that should help you out. Now, if you are told that you need to use only NAND gates or NOR gates, then you can play with that as well. So if we look at this, and again I'm going to keep F equal sigma 1, 3 equals pi 0, 2. I'm going to erase everything here. I'm going to go back to the non-inverting outputs. So y0, y1, y2, y3. And if I have to use a NOR, it would be represented like this. An AND would be represented like this, which is also this. These are two symbols for the same gate, which is an AND. So now if I have to implement F using an AND, I like this because that looks like an OR. And so that's going to be somehow easy for me to associate with the min-term canonical form, which is min-term 1 or min-term 3. However, I have an inversion going on here. So if I take min-term 1, invert it, pass it here, and min-term 3, invert it, pass it there, these inversions here are going to cancel each other out. And therefore, I'm going to have implemented my function f using an AND and two inverters, and it can be also an AND there. All right, if I have a decoder with active low outputs, then that means that the outputs are already inverted, so I have the inverters inside, so I can directly remove these guys here, and 1 and 3. You see that min-term 1 coming out here inverted is inverted again here, so these two inversions will cancel each other out. So that is equivalent to having something where I'm taking this, I'm taking that, and I'm putting it into an OR. So this part here, that the second decoder that I'm showing below, is equivalent to this one. All right, with active low outputs. All right. So something else that I want to show you that you'll have to work on, and it's right here. You have this strange decoder here, and it's actually a 4 to 10. So the reason, and some of you discovered that in the lab, is that I have 4 inputs here. Therefore, I should have 16 outputs. But that would mean if I were to implement it completely in a circuit, I would need 20 pins just for inputs and outputs, plus 2 for ground and VCC. That would be 22, and that would be too big. So manufacturers do not make decoders that big. You see here that this circuit is slightly different from the ones we've used before because it has 16 pins. So it's the first one we're using that has 2 more than regular size circuits. So what they decided to do is that they decided to decode only partly. So what you see here is that in this table is that for all these combinations of inputs that I have here, then nothing happens with the output. So it's so this part, these inputs, low, high, we're not going to see that. We're not going to be able to decode that. So the decoder decodes only partly, and it decodes the first. So this is 0 in binary, and this is 9. So it's a decimal decoder. It decodes, it understands only the index at the input that is between 0 and 9 in binary. All right. So now and this one has active low outputs. It's hard to see here, but this is what they've really showing here is 9 bar. It's another way of saying that's why 9 bar, to just simplify things. So there's a little bar over each one of these. So active low, and we see that because low means 0 and H means high. And when an output is active, it is low. Otherwise, when it's inactive, it's high. All right, so we're learning a little bit about manufacturers' data sheets. It's very good. And so if you want to use this to implement a 2-bit adder, for example, well, we know how to do that with a 2 to 4 decoder. So if I have a 2 to 4 decoder, A1, A0, and active low outputs, I know that the carry is A1 and A0, and the sum is A1 XOR A0, which is also A1 bar A0 or A1 A0 bar. So that's, what is that? That's min term 2, and that's min term 1. Sorry, this is A1, so this is min term 1. Sorry, this is min term 2. So A1, A0, that's min term 3. So min term 0 bar, min term 1 bar, min term 2 bar, min term 3 bar. So if I invert this, I get the carry, right? And if I OR, removing the inversion and using an NAND gate, then I get my sum. So check mark. We know how to implement a adder, 2-bit adder with a decoder that has active low output by using an inverter. So this inverter here, I could easily implement, of course, with a NAND gate. Okay, so now 2 NAND gates, that's it, or the decoder. So now I don't have a 2 to 4, I have this guy. And the trick is said, oh, let's see if I can recognize a 2 to 4 here. And the answer is, well, if you look at this part, that looks very much like the truth table that I have for my 2 to 4 decoder. And this part here, right here, that's the output. So what I have right here, I'm going to use maybe some green here. This and this looks like the truth table of a 2 to 4 decoder. So what I can do, so what I need to do, I know that this is going to work as a 2 to 4 decoder if A2 and A3 are 0. So I have my 4 to 10 here. I'm going to use A0 and A1. A2 and A3 I'm not going to use, but I have to make sure that they are 0. They have to be low. So in order to do that, I'm going to connect them to ground. If I connect A2 and A3 to ground, that means they're always going to be 0. So I'm transforming my 4 to 10 into a 2, 2, and I'm going to use only 0, 1, 2, and 3 output. All the others, 4 to 9, I'm going to say NC, not connected, not connected. And so I have now my min terms. I know that, what did I have here? Carry is min term 3, so I can take this, invert it, and I can take this, or it. Okay, by the way, I have little circles on all of these guys. I forgot to write them, and that's my sum, that's my carry. All right, so that should help you out with the lab.